So we need to, we may need to look at this limit at the graph, by the way. So, whoops. And in this case, well, that's like the reciprocal function, but in this case, the denominator is squared. So if we didn't have the square right here, if it were only 1, it would look like, well, vertical asymptote, so 1, 2, 3. And it would look like this, right? Shifted 3 units to the right. However, in this case, because we have a squared, we have the graph right here. Both tails of the graph pointing in the same direction, both towards the same infinity. And in this case, because on either side, on either case, the limits agree, the limit is in this case positive infinity. On the other case, on the odd exponent in the denominator where the directions are opposite, well, that'll be a DNE. Well, in the cases like we have a number over infinity, well, we're dividing by a really, really large number. We get 0. 0 over 0 or infinity over infinity. Look at end behavior, try algebra, whatever it takes in this case. And let's have a look very, very briefly at this couple of limits. Actually, they are both the same expression, but what we want to do in this case is the approach. In this case, x approaching 3, and on the second case, x approaching infinity. All right. So, well, if we plug in 3, so that's a 3 squared, which is 9, plus 5 times 3, which is 15, minus 24. So that's a 0 in the numerator, and 3 squared, which is 9 minus 9, that's 0 over 0. So this means this is good, because we should be able to use algebra to simplify these polynomials here. So in this case, limit, let's factor the trinomial in the numerator. Well, whenever the leading coefficient of a trinomial is 1, we can use the double bubble method to factor. The double bubble is this, because it's like having a couple of bubbles. Put the x's, and all we do is find factors of negative 24 that add up to 5. What are those factors? Negative 3 and positive 8. The denominator, x squared minus 9. Did you recognize the form for that one?
X plus 3, x minus 3?
Yes, x plus 3, x minus 3. That's a difference of squares, right? Boom, cancel. Limit x plus 8 over x plus 3. X approaches 3, and in this case, well, 3 plus 8 over 3 plus 3, which in this case is 11 over 6. And that's final answer. So that we get that after trying the algebra. And then that's because we got the 0 over 0 indeterminate form. Okay? So for limits at infinity, I really don't want to go through the long way. I'd rather use the shortcut here. The shortcut that you also learn in pre-calculus to find the horizontal asymptotes, because that's what limits at infinity ultimately represent, the horizontal asymptotes. And well, in this case, whenever you have polynomial over polynomial, that's the definition of the rational function, and the degrees match, we can just go with the ratio of the leading coefficients, which in this case they're implied to be invisible ones, and well, this is simply 1 over 1, which the limit is 1. If we were to do it the long way, which I'm not going to ask you to do that, you already did, you already went through that painful process in Calc 1, so it would be to divide numerator and denominator by the highest power of x that is present in the expression, right? And ultimately we should get the same answer. Okay, so that's basic limits from Calc 1, how we work with them. And the L'Hopital's rule in Calc 2, or actually I think the L'Hopital's rule is also covered in Calc 1, so But in this case, we do a few more examples. So how do we go about the L'Hopital's rule? Essentially, when we have the indeterminate form 0 over 0, infinity over infinity, shortcut, in a way we can think of the L'Hopital's rule as a shortcut to avoid a lot of algebra, and that is by taking the derivative of both the numerator and the denominator. But be careful in this case. This is not the quotient rule, right? It's just the derivative of the numerator and the derivative of the denominator. And well, in this case, as an example, polynomial over polynomial, well, what do we have? 3x squared plus 6x minus 1. Well, we have infinity. So this will for sure be the infinity over infinity in indeterminate form, right? That means that we can use the L'Hopital's rule. Let's denote LH. Let's use LH to denote that we're using the L'Hopital's rule. So if we take the derivative, limit x approaches infinity, that'll be 6x plus 6 over negative 4x. If we try to compute this limit again, that'll be again 6 times infinity plus 6, that's infinity over infinity. Well, it could be a minus or plus, it doesn't matter. That means that we can use L'Hopital's rule again. And to do that, limit x approaches infinity, that's the derivative of 6x is 6, the derivative of negative 4x is negative 4, and well, in this case the limit is negative 3/2. Alright? We could have done this using the shortcut rule because we have the same degree in the numerator and denominator, right? So the leading coefficient is 3, the leading coefficient right here is negative 2. And so the result is consistent either way, whether the shortcut rule for asymptotes or the other one right here. Let's do a couple more. Okay, so 4 times 0, which is 0, over e to the 2 times 0, that's e to the 0, which is 1. 1 minus 1, that's 0. That means we can use the L'Hopital's rule here. So let's differentiate numerator, which is 4 over 2e to the 2x minus the derivative of negative 1, which is 0. So in this case, that's 4 over 2, which is 2, and e to the 2x, x approaches 0. And in this case, we can just plug in the number. Hopefully we get a limit. Well, that's 2 e to the 2 times 0, and that's 2 over e to the 0, which is 2 over 1, which is 2. And let me just go through letters here. I know we're 1 minute to finish the class, but that's actually my main objective in this case. Okay, so limit ln of x e to the x. So ln of x at infinity, what's its value? Infinity. E to the infinity, infinity. So that's an indeterminate form. This is a good candidate for L'Hopital's rule. And let's denote, I didn't denote it here, LH. LH. The derivative of ln x, isn't that 1 over x? And the derivative of e to the x, e to the x itself. So let's rewrite this funky fraction. Let's have this x in the denominator. That's limit of 1 over x e to the x. X approaches infinity. And what would be this limit in this case? 0, because, I mean, infinity in the denominator, so 0. And we're done.